And we're sitting at 10 a.m. So if you want, we could want to give it a go?
I think we should get started. What do you guys think? Okay. All right. I can't hear you. Okay, so welcome everybody to Eric Gagliano's PhD defense. It's great to see you. Thank you. Okay. Yeah. So my name is David, David Sheen. I'm Eric's PhD advisor. I'm the chair of the committee. So a few quick logistical things. So how this is going to work, Eric's going to give a public presentation for about 45 minutes. And we'll have open kind of questions and discussion with all of you here and all of you there online. And then we'll ask folks to leave and we'll continue with the closed session with the committee. Okay. So it's my pleasure to introduce Eric. He did his undergraduate at UT Austin in computational engineering with a certificate in humanitarian engineering. He finished in 2020. While he was there, he worked with Ann Chen on satellite interferometry for looking at ice flow of the Greenland ice sheet. And he applied for and received the NSF Graduate Research Fellowship Program, which is a very selective, prestigious program. And he joined us here at UW in the fall of 2020, which some of you may remember was kind of a weird time to start a graduate program or just generally be alive. But he fit right in and he hit the ground running and was immediately, a valuable member of our team. In the past 5 years, he's pursued excellent research, focusing on satellite, synthetic aperture radar, remote sensing for snow. He's going to tell you all about that, so I'm not going to get into it. He doesn't have time to tell you about all the kind of technical accomplishments. The amount of work that's required to do this, the behind the scenes things, all of the kind of debugging code and scaling and cloud computing, that's not the stuff that bubbles up to the top in terms of science and impact. But I'm so impressed with the work that's been done. Just know that like years of really top-notch engineering has gone on here to build these things. He's also released many open source tools, including a package called Easy Snow Data. It is very easy. Some of you may have used it. It is very easy, and I continue to use it, and it's a valuable resource for the community. So he's done great science, which you'll hear more about. He received the Outstanding Student Presentation Award at the Fall AGU meeting in 2023. He has been a member of, I think he's a co-author of 5 papers in either at various stages of publication, some published, some in the works. That's independent of what he's doing here. So he's working with other people in the community, building these collaborations and working with them to do better science. Service and commitment to mentoring others has also been a huge, important theme for Eric over the years, starting with high school students. Okay, and Eric is committed to fixing the leaky pipeline. If you don't know what that is, ask him about it. He would love to tell you about it and what you can do to help. He's also helped students navigate applying for graduate school, applying for fellowships, and he's been a valuable member of our community here at UW and CEE, welcoming students, serving in committees and other things. Again, stuff you're not going to hear about today. That's why I'm telling you. If you know Eric, you know he's passionate about teaching. Okay, beyond the research. He took every chance he could to TA while he was here. Sometimes I was like, no, don't do that. He really wanted to do it. It's not because he had to. It's because he really wanted to build those skills and also to have an impact in the classroom. And the last 2 years, he's been the lead instructor of the geospatial data analysis class, which is a grad and undergrad level class. And a lot of the stuff he's done here was kind of, it stems from some of the ideas in there, and he's improved the material far beyond what I could ever do. During teaching, he's gone above and beyond. So far as even preparing lab exercises from the hospital. Yeah. You're committed, man. I mean, and he's a natural teacher. I don't know if any of you have had the opportunity to like be in the classroom with him, but I've learned a ton from Eric over the years. I'm sure many of you have as well. A couple other thoughts. Eric is contagiously positive. He's incredibly inclusive. He's incredibly generous and thoughtful. Generally just spreading love and joy in the world. I don't know if people agree with me, but that's been my experience for the last 5 years. Little things like coming to your office on a rainy Monday morning and finding an Easter egg in the nook of your door full of candy. Or a Valentine's card slipped under your door. Or a birthday card. or just other treats. And another one that stands out is when we lost our dog Penny, Eric was there within 24 hours with something that was like, I don't know what it was, but it was lots of caramel and lots of chocolate. And it was exactly what we needed at that moment. So as a final vignette, I have one more thought here. So we do this annual trip up to Easton Glacier on Mount Baker, where we go and fly drones. And every year I bring, he's chuckling, he knows what's coming. So every year I invite the new students to come, and the year Eric came, we hike up. I don't remember how many people were in the group, but we hike up there. It's 3 miles up, and then we drop our packs, and it's like time for a snack or lunch, right? And I usually try to bring some like shortbread cookies or nuts or something. And I start pulling that out and offering it to people. And Eric just starts unloading Tupperware from his backpack. And in the Tupperware was 2 Costco cheesecakes. 2. Okay. And I don't know if any of you have had this, but they're not light. It's not like backpacking food. Okay. And so we all like had a sizable piece of this cheesecake, and there's no way we could finish it. And so for the rest of the day, as hikers would come by, Eric was just flagging them down and offering them cheesecake on top of a mountain. Classic. And it's a legend at this point. So I'm going to turn it over here, but I just want to say I'm really impressed with how Eric has navigated the last 5 years, the life stuff, the work, the community, everything. And he's incredibly committed to taking care of others and himself. And just a final thought, he's one of those people who will be there for you, no matter what. And that's like increasingly rare in the world, and I honestly can't say the same for myself all the time. So, I appreciate that. So please join me in welcoming Eric Gagliano. Thank you.
Wow, thanks, David. That was really beautiful, very touching. Cheesecake story is true. Unfortunately, no cheesecake now. Found out I have celiac disease and diabetes, so probably not the smart call. Okay, I'm just gonna reset the timer here. So I got 45 minutes to present this stuff, so let's see if we can get through it. So thanks everyone for coming to my PhD dissertation defense. The title of my talk is From Peak to Climate, Advancing Multi-Scale Detection of Snowmelt Timing with Satellite Radar. Before we get into the chapters of my dissertation, we're going to begin by motivating this work, introducing some of the core concepts, and laying out the objectives. So seasonal snow accumulates in the winter and melts in spring and summer. We can watch its usual progression here in this video. We start in October, and as we enter the winter, snow begins to advance across the northern hemisphere, covering nearly half of the northern hemisphere by February and March. Then snowmelt begins, and then snow cover retreats back up to the poles into the higher elevations. And while we're experiencing summer, the southern hemisphere is experiencing winter. They experience the timing opposite to us. So for them, the snow advances to their maximum around August in the Andes, Oceania, and small parts of Africa. Seasonal snow is essential to the Earth system, and then more than 1/6 of the world's population relies on runoff from seasonal snow and glaciers for agricultural and domestic water supply. Since we rely on seasonal snow for so many applications, including domestic water use, dam operations, flood management, ecosystems, and as indicated here in this figure, irrigation, understanding snowmelt timing is important because it controls when we receive this critical resource. If you look at where we live, we can see some darker blues, indicating greater reliance on irrigation from snowmelt. In fact, in California, in the San Joaquin River Valley, more than 70% of the water is used for irrigation, which comes from the snowpack of the Sierra Nevada. This pattern repeats globally in high mountain Asia, the Andes, and other mountainous regions. So let's take a little look at an illustration for how snowmelt turns into streamflow. We have our mountain snowpack with snow monitoring station that measures the amount of snow, and a stream gauge downstream that's measuring stream flow. So we measure the amount of snow as snow water equivalent, or SWE. You can just say SWE for short. which is the amount of water if we melted down all of the snow into water. And here's the progression of an example year. As snowpack accumulates through the winter, you see SWE increase over time. And when melt begins, SWE decreases. You can note the progression of water in the snowpack with these icons. The dry snow is white and the blue is wet. Once the snowpack has warmed and fully ripened, as we call it, any additional energy will cause water to come out of the snow. So this is runoff onset when water begins leaving the snowpack and entering streams. There's some extra complexity there that we're kind of glossing over. But here's another example of a year with a different amount of SWE and later melt. You can also see the snowpack getting wetter, especially once you get to maximum SWE. And from that point forward, water starts to leave the snowpack. We'll see in the rest of this presentation that the year-to-year variations in runoff onset timing can be high. And we'll be calling this interannual variability instead of year-to-year variability. And understanding the timing of this is critical because that determines when downstream populations have increased water availability. But snowmelt timing varies dramatically in space and time. Spatially, for a single mountain range, snowmelt timing can vary by months from low to high elevations, 20 to 40-day differences in melt timing, usually between sun-facing and shaded slopes, depending where you are in the world, and several months of difference between mid-latitudes and polar latitudes, as we saw in that first video. We can observe interannual variation in snowmelt timing for the same location. Snowmelt timing can shift over a month, largely due to winter and spring synoptic scale meteorology. Synoptic scale meteorology includes weather systems like high and low pressure areas, fronts, mid-latitude cyclones, etc. Of particular importance for snowmelt timing is the advection of warm, wet air masses in the spring, which often accelerate melt, as well as large winter storms that build up the snowpack in the first place. Here we can see the Sierra Nevada around April 1st of 2020, 2021, 2022, 2023. And we can see different snow volumes built up over the winter. So this is taken around the same time of year. This is around April 1st, usually when snow is reaching its maximum at this area in the world. And we see very different volumes for these different years. And part of that has to do with synoptic scale meteorology in the winter that builds up these snowpacks in the first place. So to complicate things further, variable synoptic weather patterns interact with fixed topography to create even more complex spatial and temporal variability. And all of this variability matters. It determines when water becomes available for over 1 billion people. Current observation techniques struggle with these complexities. So to understand and manage these resources, especially as climate changes, we're going to need more systematic high-resolution observations. But here's something remarkable. Despite temporal variability, spatial patterns repeat. This is the same location in the French Alps, 124 years apart. On the left, you have that postcard from 1900s, and then in 2024, that picture was taken with the postcard. And we see the snow distribution pattern is strikingly similar. Low elevations are snow-free, and high elevations and north slopes maintain cover. This repeatability also exists at larger and smaller spatial scales and reveals systematic physical controls, elevation, slope, and terrain aspect at this scale. If patterns are systematic, we can understand them globally, but we need consistent observations. Beyond the year-to-year variability in snowmelt timing, we've observed long-term shifts as well. In this figure here, snow monitoring stations across the Western US are showing peak snowpack occurring around 8 days earlier since 1982. The larger the pink marker box, the larger the trend towards earlier peak snowpack and snowmelt. You can see these trends towards earlier melt are particularly strong within the upper Colorado River Basin. And other projections for the Western US suggest snowmelt timing could shift up to a month earlier by 2050. This makes systematic monitoring even more critical. So for populations dependent on snowmelt water resources, we need to ask the following questions. What are the topographic controls on snowmelt runoff onset, and how do they vary globally? Where is interannual variability highest? And which mountain ranges are most vulnerable to climate warming? To answer these questions, we need repeated systematic observations across Earth's diverse mountains, as we just discussed. But this requires a consistent methodology, high-resolution data that captures the terrain complexity and global coverage and multi-year records. So a lot going on there. This was previously something impossible. Regional studies use different methods, and large-scale models tend to get snowmelt timing. Current techniques are unable to fill the requirements for this sort of data set. In situ snow monitoring stations are sparse and miss local spatial variability. While we have an impressive snow monitoring infrastructure in the Western US, primarily the SNOTEL network, other snow-covered regions lack consistent and widespread monitoring. Take note of the snow pillow sitting on the ground beneath the tower. That's instrument measures SWE. It's called snow pillow. We're going to see it pop up again pretty soon. Optical remote sensing cannot penetrate clouds, and unfortunately, clouds are very common during the melt season, as you can see in the stretch of cloudy images over Mount Rainier. And passive microwave remote sensing has 25 kilometer resolution, so that's far too coarse for mountainous terrain. In order to understand snowmelt timing at high spatial resolutions, we also need high spatial resolution observations. So C-band synthetic aperture radar, or C-band SAR, solves this. SAR is a type of active remote sensing that transmits and receives microwave pulses. The received pulses we call backscatter, and it's this backscatter that we use to infer physical properties of surfaces below. So C-band refers to the specific microwave wavelength that's used, and it's this wavelength that determines many of its powerful properties. Here's an optical image over Mount Rainier. Optical sees only clouds. However, on the same day, here's a SAR image from the same time and same location, roughly. The SAR image captures details over Rainier. The values in the images in the image is called backscatter, and in this color space, brighter colors represent higher backscatter and darker colors represent lower backscatter. Notice that SAR is not necessarily measuring what our eyes can see, but SAR is especially powerful because it can capture high resolution images day or night and also penetrate the cloud cover that optical remote sensing suffers from. But even more critical to our applications, SAR is sensitive to liquid water and snow. When a snowpack is dry, C-band radar can penetrate through the entire snowpack, and strong backscatter signal comes from the snow-ground interface. In fact, in dry snow, for lack of a better metaphor, C-band SAR is practically invisible, or snow is practically invisible to C-band SAR. But when liquid water appears in the snowpack during melt, it dramatically changes the snow's interactions with microwave energy. The C-band signal is absorbed strongly, resulting in much weaker backscatter. A lot more complexities there again, but we're just gonna kind of gloss over that for now. This dramatic contrast enables us to detect when snow transitions from dry to wet. So the Sentinel-1 mission provides exactly what we need. To the right, we're going to have this artist's rendition of a Sentinel-1. Oh, no. There was a challenge again. Oh, it worked. Whew. So we're going to have this picture of Sentinel-1, an artist's rendition of Sentinel-1 capturing the SAR image as it goes along. So Sentinel-1 is a constellation of C-band SAR satellites in polar orbit, giving us consistent global coverage. And the polar orbit just means that we're imaging at consistent local times, so approximately 6 a.m. or 6 p.m. The spatial resolution is 10 to 20 meters, and critically, all data since October 2014 is freely available. Each satellite completes a full orbital cycle every 12 days, and when 2 satellites are operational, we achieve 6-day repeat coverage. The number of satellites in the Sentinel-1 constellation has changed over time, and you already saw the big reveal here. Sentinel-1D reaches orbit, and that was last week because I guess, yeah, 4-11, they do dates backward over in Europe, which is something that I've struggled with. So now bring the number of operational satellites to 3, at least for the time being. We'll see how long Sentinel-1 lasts. So this is going to be our tool that we use for global monitoring. So with our knowledge of SAR interactions with wet and dry snowpacks, let's just interpret some snowmelt progression over at Mount Rainier. So again, there's a little diagram. And we also have some average daily air temperatures at Mount Rainier. So starting in January 2020, here's a SAR image, and we see bright colors for the most part, which represents high backscatter, indicating dry snow. And up until April, we see temperatures mostly below zero. So that makes sense. We see the SAR images relatively stable. But after this point, we see that the average air temperatures increase over 0 degrees. So what would we expect in this next image? You see at the lower elevations, you see a lot darker backscatter, darker values, so lower backscatter. So that indicates the presence of liquid water in the snowpack. And then for the rest of the time series, you can see how the darker values progress up the mountain. And for us, that means that melt is happening at higher and higher elevations. So we'll return to our illustration for some final checks with C-band SAR and what it can tell us. So we'll also add a graph of C-band SAR, coincident in time. And what C-band SAR is going to help us do is delineate snowmelt phases. We mentioned earlier that we're primarily interested in snowmelt runoff onset, which is when the snowpack has warmed and any additional input energy is going to lead to water leaving the snowpack. So the snowmelt runoff onset date has important implications to us because it marks the start of increased water availability. And the key insight here is the backscatter minimum of the time series of backscatter marks the transition to runoff onset, which is also when water begins leaving the snowpack. This is a relationship that has been validated against snow pillows, snow pits, and stream flow, and we'll leverage this globally to map snowmelt runoff onset. First, we're going to start in chapter 1, though, with a little proof of concept. So this brings us to our overall motivating question. For the over 1 billion people depending on snowmelt, what controls snowmelt runoff onset timing, and how do these controls vary globally? My dissertation addresses this in 3 chapters. Chapter 1 develops an improved SAR approach for runoff onset detection and demonstrates its applications in the Cascade Range. Chapter 2 scales this method globally, creating and validating a 10-year high-resolution global runoff onset dataset. And finally, in chapter 3, we're going to get to analyze the spatial and interannual variability of snowmelt runoff onset across the Earth's major mountain ranges. Okay, so the first chapter is titled Capturing the Onset of Mountain Snowmelt Runoff Using Satellite Synthetic Aperture Radar. So we developed some methods and tools for high-resolution snowmelt timing analysis, and in the process, we're going to answer a couple questions. 1, how do we improve existing SAR methods to better quantify when and where snowmelt runoff onset occurs? And can we quantify topographic controls and interannual variability with high-resolution runoff onset maps? So we don't have to spend too much time on this slide, but just briefly while we focused on the Cascade Range stratovolcanoes, they span around 3,000 meters at least of elevation. They're distributed across a gradient of latitude. They have a roughly conical shape, which is going to help us systematically analyze aspect and slope differences. Lower forest cover reduces C-band SAR interference. Large average annual accumulation provides a range of different snow conditions, SWE values. And all of these characteristics together, we expect a large range of potential runoff set dates. It's a good laboratory to start. So in our method shown in the graphical form here on the right, we prepare a time series stack of Sentinel-1 images and locate the backscatter minima at each pixel location. We start with images from different relative orbits or exact repeat orbits of the satellites, which means they have the same viewing geometry. And each relative orbit is represented with a different color border. Then we build a backscatter time series of each pixel and estimate the timing of the backscatter minima at each orbit, represented by the dashed vertical lines. And then we take the median of these dates, which corresponds in this case to April 25th. Combining estimates from different relative orbits was a unique contribution of ours that improves the accuracy and temporal resolution. So we place that date in the snowmelt runoff onset map for that pixel, and then we do that for every pixel in the SAR image. And as expected, we see lower values corresponding to runoff onset in April at the bottom of Mount Rainier, as anticipated in that little schematic that we went through. and a later runoff onset in June and July at the higher elevations. So let's look at Mount Rainier results in a little bit more detail. The top row shows annual runoff onset maps for 2015 through 2022. You can see the characteristic elevation gradient each year, with melt at lower elevations progressing to melt at later elevations. And from these 8 annual maps, we can calculate this 8-year median, and that's to represent the typical runoff onset timing, reducing the influence of anomalous years. So we then can calculate how each year deviates from this median, creating these annual anomaly maps. Blue indicates later melt relative to the median, red indicates earlier melt relative to the median. So 2015 stands out dramatically. Almost the entire mountain shows 25 days of early melt at least, coinciding with the 2015 snow drought here in the western US, which we'll talk about again later. Finally, we calculate the median absolute deviation. So this is where timing is going to be more consistent versus variable year to year. So most of the mountain shows 5 to 15 days of variability, with the lowest variability on the exposed slopes. To validate this approach, we compared our runoff onset estimates to snow pillows, which measure SWE at 5 nearby snowtel stations. Here's our illustration of runoff onset timing again. And we extracted the median runoff onset date from our maps within 500 meters of each snow pillow, represented by that dashed circle. For the snow pillow estimate, we used the last day SWE was above 95% of its maximum. Using this threshold instead of just the absolute maximum reduces the potential for false identification of runoff onset that has to do with processes like wind redistribution or sublimation. And if you want more details on this choice, that's something we can talk about during questions. Across all 5 years, all 5 stations over 8 years, we found a median offset of just 1 day and a median absolute offset of 10 days. This agreement gave us confidence to interpret these results. We took the median map for all 10 of the sampled stratovolcanoes, and you can see those stratovolcanoes in that plot inset there. This plot has elevation on the y-axis and median runoff onset date on the x-axis. So this plot shows that for every 100 meters of elevation gain, the observed median delay in runoff onset was 4.9 days later. The general trend of later melt at higher elevations is relatively intuitive, but the specific rate had not been quantified at high resolution up until this point. These runoff onset elevation gradients are relatively consistent across all stratovolcanoes, as indicated by the lines having similar slopes. So in chapter 1, we developed and validated a scalable SAR method to map runoff onset. And we quantified runoff onset spatial and interannual variability across Cascade Range stratovolcanoes. The first chapter was published in Geophysical Research Letters in November 2023, so please check that out for more detailed explanations and analysis. Now we'll move on to chapter 2. So we successfully demonstrated the method in the Cascade Range, but that's just one small region. We want to eventually answer whether the spatial and temporal variability we identified in chapter 1 can be captured elsewhere. To truly understand global runoff onset patterns and their controls, we scale this approach to all seasonal snow on Earth. So in this chapter, we're going to ask, how can we scale our methods to create a global runoff onset data set? And how does our runoff onset data set compare to runoff onset estimates from in situ observations? So scaling globally presents 3 major challenges. First, C-band SAR is sensitive to snowmelt, but not snow presence. Dry snow is essentially invisible to C-band, as we mentioned. It looks about the same as bare ground. This means we can't use SAR alone to know when and where to search for runoff onset. Second, we're dealing with over 100 terabytes of Sentinel-1 data, and traditional processing approaches are simply not in scale. And finally, Sentinel-1 coverage and revisit frequency varies dramatically by location and time. So here are 2 observation plans that dictate where Sentinel-1 acquires data. So the green diagonal lines represent 12-day frequency. The red diagonal lines represent 6-day frequency. And on the left, you can see on the left observation plan, you can see when there's one active satellite in the constellation versus a plan where there's two active satellites on the right. So with two satellites, we had full coverage, achieving 6-day exact repeat in some locations, as you can see with the red. But on the left side, there's often areas that are just not covered at all, like Northern Asia. So our methodology needs to be able to address these three challenges. So here's how we solve those. So we're going to walk through our workflow using Mount Rainier as an example. There's a lot going on here and a lot that we kind of simplify for the presentation. So please feel free to ask questions about this. So addressing the snow presence challenge, we created a custom snow phenology dataset from MODIS optical imagery that we cloud filled. Snow phenology refers to the annual cyclical changes in snow cover. So it includes 3 key variables: consecutive snow days, snow appearance state, and snow disappearance state for each year. This dataset is valuable in its own right, but for now, it defines the temporal window where we should search for runoff onset in the SAR data. Second, addressing the processing challenge. We partition the globe into nearly 24,000 tiles, each about 160 kilometers across. We do this to process each tile independently, so we can use distributed computing libraries like DAS. So for a given tile, we're going to query both the snow phenology dataset and all available Sentinel-1 data. And then for each tile, we will complete this runoff onset identification process. So we group the Sentinel-1 data by the relative orbits, as we did in Chapter 1. Remember, different orbits means, relative orbits means that those are different viewing geometries. We first remove orbits with insufficient revisit, addressing the coverage variability challenge. So removing orbits with any gaps greater than 30 days between individual repeated overpasses. So for each pixel with 56 or more consecutive snow days, as identified in the snow phenology data set, feel free to ask about that threshold later. We build the backscatter time series for each orbit with its own color, red, blue, or green here. So using the snow phenology appearance and disappearance states, we search only the latter half of the snow-covered period. This avoids false detection from early season melt events. So similar to Chapter 1 then, we take the median of the dates of minimum backscatter for each of the orbits, and then we insert that median date as our final estimate into a specific pixel in the tile. So this multi-orbit approach improves both temporal resolution and increases robustness to things like rain-on-snow events. For every tile, we then insert that into the annual global runoff onset data set. Once we have all of the years built up, we can take composites. So like that 8-year median we did in Chapter 1, we can do a 10-year median instead with this 10-year time scale. And we can also look at things like the median absolute deviation, which, calling back to Chapter 1, that was kind of to look at the interannual variability. So the year-to-year differences in runoff onset timing. So here's the results. 10-year median runoff onset across nearly all seasonal snow on Earth at 80 meters resolution, covering 43.7 million square kilometers. Note that since the northern and southern hemispheres experience opposite seasons, the color bars have 2 months, and the top one is for the northern hemisphere, italicized, bottom one is for the southern hemisphere. In the northern hemisphere, we see systematic progression from early melt at lower latitudes and elevations, starting in January and February, all the way to higher latitudes and elevations into May, June, and even July if you zoom in. At first glance, the spatial patterns are coherent and follow predictable gradients. Note these gaps over here. Those reflect spatially varying Sentinel-1 coverage, one of those challenges that we talked about, as well as data quality filters. Antarctica and Arctic islands are missing because Sentinel-1 uses a different acquisition mode over these areas. So let's zoom in order to just appreciate this resolution. So as we zoom into the cascades, if we have any cascade enthusiasts out there, feel free to shout out where you think we're zooming into based off of runoff onset map alone. If you're here in person today, that's where we are in Seattle. So we'll zooming in so you can see what 80 meters actually looks like. Zooming in from global scale. Any guesses where we are? Who said that? So did someone just say Glacier Peak? Someone said Glacier Peak, right? Yay, yeah. So it's Glacier Peak. That's really impressive. And one of the things that's really cool about navigating these maps is they often look like digital elevation models. So just kind of like an elevation a map. And that also kind of helps with navigation sometimes, but that also just represents how strong those elevation gradients for runoff onset actually are. So for Glacier Peak, we can see that the medium runoff onset dates predominantly occur in May through June. Okay, so to put our spatial resolution in context, let's compare it to passive microwave remote sensing, the previous best option for large-scale melt detection. So we're going to focus on the Alaska range for 2020. And this top plot shows especially downscaled passive microwave product at 6.25 kilometer resolution. So this is actually better than the standard 25 kilometer products. And notice the lack of variability with elevation. It essentially just shows melt ending by April all across the entire scene. However, our product at 80 meters tells a very different story. We see strong elevation gradients, melt continuing well into July at higher elevations. The passive microwave product fundamentally cannot resolve this mountain terrain complexity. We can do a quick difference map between these two. And the difference map shows where the products have different values. So at high elevations, we're detecting melt 75 days later than the passive microwave product. And the histogram of the difference map shows our product is typically 5 days later on average, but with a standard deviation of 31 days. So that reflects how passive microwave smooths over the true variability. Though these products measure slightly different things, we're encouraged by the fact that the bias in this comparison is relatively small. And the comparison is actually quite generous to passive microwave remote sensing because this is a downscaled product that only currently exists for Alaska and parts of Western Canada. Globally, you'd be working with 25 kilometer resolution, and our 80 meter product represents a 300-fold improvement in spatial resolution. So now let's do a more formal validation of this data. So to validate this data set, we take a similar approach to chapter 1, where we compare our runoff onset estimates to snow pillow derived runoff onset, but expand our coverage to a 1,000-meter buffer around each station to account for larger pixels and increased forest cover. So here we've computed the difference in estimates by year. Understanding how these estimates vary by year is important because our temporal resolution is dependent on the Sentinel-1 observation plan for that year or for that time. And the number of orbiting satellites. Generally, the years with the largest spread of differences tend to be years with only one operational satellite, like 2015, 2016, and 2022. Even so, the differences aren't huge, and we feel pretty confident with our results because we observed biases around a couple of days and a median absolute differences ranging from 7 to 14 days, depending on the year. We also computed the median difference at each station to give us some indication of estimate agreement by station. So though we observe low biases in most locations, we notice a cluster where our product often indicates runoff onset earlier than the stations, which shows up as these dark red circles in the east. These are areas where forest cover is high and maximum SWE values are low. So this makes sense because C-band radar cannot reliably penetrate the densest forests, and we've empirically found that SWE below 20 centimeters doesn't produce as large of a backscatter drop. Overall, our validation effort showed strong agreement with median differences of 1 day and median absolute differences of 9 days. And though we're more systematic about it and go into more details and complexities in the paper, we show that our data set performs optimally below 50% forest cover fraction, above 20 centimeters of SWE, and temporal resolutions better than 14 days, which isn't too hard in this area of the world. So this data set has many use cases, and many researchers have already been using these tools and data in many interesting applications that supplement also as a form of validation that we don't really include it since it's their work, but definitely something interesting to look at. Lila Rickenbaugh from Montana State University combined in situ collections of stable water isotope ratios and our SAR snowmelt timing tools to investigate the relative contributions of snowmelt and groundwater to irrigation supply in southwestern Montana over time. Among other cool results, Lila found that the relative contribution of snowmelt to streamflow peaks soon after our tools predict runoff onset. Barira Mirza, who's here today at Oregon State University, used our data set to show that streamflow in snowmelt-dominated watersheds in the Sierra Nevada shows strong relationships with the number of pixels experiencing runoff onset. She evaluated the lag between snowmelt and streamflow response with implications for streamflow prediction. Ali Dietrich at Colorado State University used these tools to demonstrate the relationship between the SNOTEL soil moisture pulse and runoff onset, finding a median difference of 3 days and a standard deviation of 25 days. So going beyond this runoff onset identification idea of just looking at SWE values alone, but actually looking at when water goes into the ground. Pritika Kaur at University of Wyoming leveraged our runoff onset data set to constrain when and where L-band instar SWE retrievals methods are likely to succeed, and the feasibility map she produced offered practical guidance for researchers and practitioners hoping to leverage new L-band missions like NISA. We don't have time to mention all the applications of the data set and tools so far. These are ones that I think are particularly relevant to this idea of validation and what runoff onset is actually telling us. But other applications include things like forest snow interactions that pilot Christopher Moody and Mary McDonald are working on. So to summarize chapter 2, we created the first global high-resolution runoff onset data set by processing over 100 terabytes of Sentinel-1 data. We validated against almost 5,000 station water years, over 900 automated weather stations, achieving a median difference of 1 day and a median absolute deviation of 9 days. And we identified environmental controls on this data set, so where this data set performs best. Now we can use this data set to understand some global patterns. So now we can start to answer the questions that we posed in the beginning. What are the topographic controls on snow runoff onset, and how do they vary globally? Where is interannual variability in runoff onset the highest? And which mountain ranges are most vulnerable to climate warming? For the first time, we have globally consistent observations to answer these questions systematically. And before we jump in to some of this, we just thought we'd quickly just mention again what the controls on snowmelt timing are. Energy balance involves many factors, so solar and long wave radiation, sensible latent heat fluxes, and so on. But geography, climate, weather largely govern these factors. So we're going to focus on those key variables since we can systematically observe those. So we're going to look at latitude and elevation on all seasonal snow, and then look at elevation and aspect and climatological variables for individual mountain ranges. So here's the 10-year median runoff onset data set again with some zoom-ins of some different areas. And just at first glance, we can see some elevation and latitude gradients if we kind of squint, but we wanted to quantify this by aggregating into elevation and latitude bins. So what you're about to see here is the plot on the left is the same median runoff onset. And then the plot there on the right shows for that area of the world, the aggregation of the runoff onset date by latitude and elevation. And to the right, the other plot was the median absolute deviation aggregation. So again, that's just showing what does variability usually look like, interannual variability usually look like in these areas of the world. And so we have that for these 6, all the continents, except Antarctica. So we observe latitudinal gradients below 5 days per degree latitude increase in Asia and Europe above 55 degrees north, indicating rapid runoff onset above this latitude. And we also see elevation gradients tend to be strongest at mid-latitudes, indicating that runoff onset shows larger delays for increase in elevation. We also note just some interesting areas of high interannual variability, like the tropical and subtropical Andes, which we can get more into later. But what this type of aggregation does, though, it kind of glosses over some of the mountain range differences. So a maritime range like the Cascades and a continental range like the Rockies are going to behave very differently, even though they're at similar latitudes. So to understand that variability, we aggregated by mountain range. I'm not going to go into too much details about that aggregation, but we use this specific mountain inventory. We use this to quantify different topographic controls, as well as some climatological variables. So if you remember back to chapter 1, we calculated runoff onset delay with elevation gain, and now we can do this globally. So let's see what patterns emerge. We see widespread runoff onset delays primarily between 2 and 6 days delay per 100 meters of elevation gain. And we see a median runoff onset delay of 3.5 days per 100 meters. So if you remember back to chapter 1, we saw this rate was 4.9 days for the Cascade stratovolcanoes, for context. We also saw that mountain ranges with lower delays are primarily in polar latitudes or have little relief. But elevation is only part of the story when it comes to topography. So in order to evaluate elevation and aspect simultaneously, we looked at these polar plots, which together we just call triplet plots. So think of them as looking down at a mountain from above. The radial position represents elevation. So the outermost edge is 0 meters of elevation and the center is 7,000 meters. And the angular position is going to represent terrain aspect. So which side of the mountain you're on, north, south, east, west, respectively. The next panel is going to show us, or the variable that's plotted on here is the 10-year median runoff onset timing that we've seen. So it would make sense to see the highest melt in the center because that's the highest part of the mountain. The next panel is going to show us the median absolute deviation in the same binning scheme. Again, higher values, higher interannual variability. And then this final one is particularly useful. It shows the elevation normalized timing, which isolates aspect effects by showing how each aspect elevation combination deviates from the elevation band median. So in the northern hemisphere, that's basically saying that we expect this darker red area to be on the south side, which it is here, saying that melt's happening earlier on the southern aspects, particularly here around 3,500 meters. So the next slide, we're going to place the triplet plots over the runoff onset elevation data. And there's a lot going on here, so don't be overwhelmed. Just some high-level trends maybe to point out. The center panels show interannual variability, and this varies substantially from different ranges. There's some ranges where there's 10-day median absolute deviations, like the Ural Mountains, and there are places like the Chongtong Plateau that have over 30 days of interannual variability. So high elevation and high mountain Asia. And aspect control shows some expected patterns in most ranges. So in Northern Hemisphere, you see the red on the southern side, meaning melt happens earlier there. And the typical maximum difference is around 10 to 40 days. And more to talk about there, but we're running short on time. So some other important things to talk about. So if you remember our annual runoff onset anomaly, we also looked at that globally. So we can just briefly step through some of our mountain range level anomalies. We can see in 2015, what really stands out is the Western snow drought that we mentioned. You see particularly high variability in the tropical and subtropical Andes. And then in 2022, you see high mountain Asia has this really, really early anomaly of 30 days or more, and that coincides with a mega heat wave they experienced. And the western US, the Sierra Nevada snow deluge is there, and also the mega heat wave that affected Europe in 2024. So we're interested in looking at some of the variables that cause this interannual variability. So we focused on some ERA5 land climate reanalysis data set in order to tease apart some of these forcings. And we considered lots of variables across different seasonal windows, but we were focusing on average spring 2-meter air temperature for now. And so here's the Sierra Nevada for 2015 to 2024. This is the median runoff onset. We're going to show how each year's runoff onset anomaly next to it. So we can see in 2015, the snow drought, you see 38.5 days earlier mean anomaly. You see in 2023 with the snow deluge, you see melt happen later. But we can also plot the ERA5 spring land temperatures there and see those anomalies. And we can see how those anomalies match up against each other. And there's some inter-mountain range variability, but as a first pass, you can take these mean values and you can put them on a plot to see their relationship. And then you can draw a line and show that you fit a line using linear regression or even more robust metric like send slopes. And you see correlations of 0.88, a slope of 13.3 days per degree Celsius. So what that's telling us is that for every extra degree warmer of spring average air temperatures, we see runoff onset timing shift 13.3 days earlier. So we wanted to know if we can observe this for other mountain ranges. So we plotted that sensitivity and we looked at surrounding mountain ranges and saw that at similar latitude, we have similar sensitivities here in the Western North America. But as we go up in elevation, that process weakens because melt happens later in the year and they're more radiative process driven. We looked at the rest of the Earth's mountain ranges and calculated sensitivities for 150 mountain ranges that we looked at, and the opacity of the polygons is showing us correlation strength. So polar ranges appear faint with low slopes and weak correlations, which makes sense to us because by the time those snowpacks melt in late spring, solar radiation is already intense. So removing some of the clutter, what we saw was the strongest sensitivities, -5 to -13 days per degree, appear in mid-latitude and coastal ranges. And these regions show both high sensitivity and strong correlations. And the analysis could inform which ranges are most susceptible to regional climate variability and trends. So because we already know in long-term observations that snowmelt timing is shifting earlier, we can look at projections in air temperature regionally from things like the IPCC report in order to think about how what ranges are going to be most vulnerable to climate warming. So on the right, you see the latest IPCC report with projected global surface air temperature changes. And if you wanted, you can multiply our observed temperature sensitivity to expected regional warming to get a very rough idea of potential timing shifts. So 1 additional degree of warming might not be super impactful for some polar range, but for the Sierra Nevada, it could mean the difference in large shifts in snowmelt timing. So the estimates are very rough and shouldn't necessarily be used for long-term prediction. They make a lot of assumptions here, but what is nice is the framework enables the first comprehensive vulnerability assessment by mountain range at high resolution. As the observation record lengthens, we're going to have even better understanding of sensitivity and longer-term trends. So to summarize chapter 3, we looked at topographic controls like elevation and aspect. We saw the most extreme interannual variability, and we also established some empirical runoff onset relationships with spring temperature. So in chapter 3, we work to quantify the spatial and interannual variability of runoff onset systematically across mountain ranges. And mountain ranges are great for documenting nuanced controls on topography and climate for over 1 billion people that depend on mountain snowmelt. For water resources, though, the most relevant spatial scale would be the river basin. So with our 80-meter resolution data, you can take a first look at what that data might look like. And because we're short on time, I won't talk about these too much, but basic takeaway here is that a lot of the high population basins in Western North America experienced in the past 10 years at least one instance of anomalies in snowmelt timing of greater than 30 days. And you also see these seesaw patterns in several years, which is also similar to some documented precipitation trends and relevant like storm tracks. Finally, you could also look at this data over high mountain Asia because we know the Tibetan Plateau provides so much water for the world's population. It's important to understand the reliability of this water's timing. And just one high level takeaway is contrasting patterns you see on different parts of the plateau. Western basins, the Indus, Brahmaputra, and Ganges headwaters show relative reliable water delivery with interannual variability of less than 15 days. And you contrast that to the east side, where you see runoff onset happen a little bit earlier, but with higher variability of 15 to 30 days. So the differences in timing have direct implications for water resource planning and infrastructure, and basins with less predictable timing may require different management strategies. So this type of information could be used to inform those sorts of analyses. Future work, not worth talking about, I think, in length, just because I couldn't stop thinking of some things that I really wanted to do, but you can break them into basic categories between extending the data set, looking at more specialized applications, connecting this to actual hydrology is something that is really exciting and a lot of people are starting to work on with this data set. So it's a really exciting time, I think, to be working with these sorts of data. So the dissertation's key contributions, the different chapters look at first prototyping this methodology, scaling it globally, and then getting to use it for some more interesting applications. And the key takeaways are we've created a high-resolution global data set enabling the first systematic intercomparison of snowmelt timing and its controls across Earth's diverse mountains. The tools and data are publicly available, hopefully for the community to use. We saw that mid-latitude ranges like Sierra Nevada display strong temperature sensitivity, negative 13 days per degree Celsius, indicating these regions could face greater vulnerability to runoff onset timing as the climate warms. Finally, over 1 billion people depend on snowmelt, face extreme interannual variability. We documented 20 to 40 day swings in timing relative to median conditions, not unlike the 2015 snow drought in the Western US and the 2023 snow deluge in the Sierra Nevada. So as climate continues to warm, these extreme shifts potentially become more common. And so systematic monitoring becomes increasingly critical for water supply. So finally, just like to do some acknowledgements. Huge thank you to the entire committee for support and encouragement. I would not have been able to get through this long process without y'all. So thank you. Like to thank the academic community, so Taco Lab and the Mountain Hydro Group, all of civil and environmental engineering, everyone that I forced to do the intramural sports with every year. I think included some pictures, but I had, I think, like 80 of those, so I didn't include all of them. Thank you to our union. I'm going to be graduating, so open spot for union steward if someone wants to do that, please sign up. And other folks are on here as well. All the people who brought me food. Michelle, who's probably cooked me 30 pounds of food at this point this past week. So thank you. Yeah, choir friends, camp friends, my Camp Castle family, I think some of these slides, especially, and my extended family, family friends. And if you're on here, if you're not on here because it's not loading for some reason, everyone, if you're just here today, thank you so much for being here and seeing this day for me. So it really means a lot. Thank you. Awesome. Well, now I'm happy to take questions for a little bit, and then after I think like 10 minutes or however long, then it's just going to be the committee. Now would be a great time for public questions. Clinton, yeah.
You were showing those like polar coordinate plots and elevation.
Uh-huh.
Do you think that it seemed above 3,000 meters, there's starting to be a big aspect change?
Mm.
Do you think that's a function of slope angle, that like higher mountains are just steeper, so they're facing more of the sun, or what do you think?
I think there are a bunch of things. One of the plots that I left out was this analysis of the difference in timing between like shady slopes and sunny slopes as a function of latitude. And one of those patterns that we saw there was kind of like this pattern that follows like a similar like day of year trend, where the maximum aspect control, tends to have to do with more about the like solar geometry and the cyclical cycles there. So where you are in relation to like the equinox or the solstice, where the sun elevation is, plays a large part in some of I think those patterns popping up. But yes, like slope plays an important role too, right? Like if you have like a 10-degree slope versus like 45 degrees, at 45 you're gonna have more of like direct solar radiation than right. Big difference there. So it's a lot of different, I think, overlapping, complicated processes going on there. Yeah, thanks so much. Harold, yeah.
Yeah, I have this question where you're receiving data from the satellite,
Mhm.
C-band radar,
Yes.
some microwave, something.
Mhm.
data. Have you ever experienced a little bit of, disalignment problem where one scan and the second scan is 1 pixel or 5 pixel off each other?
Yeah,
And how do you solve that?
I appreciate the question. So for audience online, the question was, for the Sentinel-1 data, is there like ever instances where there's like misalignment, right? That there's like co-registration issues or something like that. One of the things that's really exciting about the Sentinel-1 data is it's for a different use case where they use this process called like interferometry. They have to make sure that the like the co-registration is like really, really good. They have to make sure like the pointing is really good. So all of these like controls where a lot of other satellites, we might have to worry a little bit more about these co-registration problems. We don't see as much in the SAR data. That being said, it doesn't mean that those problems are gone. Depending on the latency of this like data product, there are different versions. So there's like these data product that might be released like 1 hour after the image is acquired. That might not have as good accuracy as one that's like a little bit later when they have a better understanding of the orbits and the pointing and things like that. It's not something that I had to run across at the spatial scales that I was dealing with like the 80 meter pixel. But yeah, definitely something to consider for the higher resolution applications. Thank you for the question. Yeah, Anna.
I guess going off your answer to the last question about the latency,
Mhm.
This seems like a really great data set for looking at trends and variability. Is it something that you can use in the current year to say, like, call farm managers and say, hey, melt onset is happening now,
Right.
put that into your model?
So Hannah just asked a question kind of about the retrospective nature of this data set. We're looking back in time at runoff onset, but like what are the applications for more like near real time application of this data? That's something that has to do more with just understanding when the snow itself is wet. So that's something that I didn't get to include here, but something that I've gotten to do a little bit of work on, of looking at like these binary wet snow maps using the C-band radar. So runoff onset is just telling us when like water is like leaving the snowpack, but we can know beforehand, right? Is the snow wet? Because you might have like this cyclical like progression throughout the melt season where it's wet, the surface is wet, then it's not, then it is, and refreezing and diurnal variations there. So that is something that you can definitely do. And I think something really exciting and something I wish I could have included, but as you saw, I already had too much, I think, in here that like I had to, crossover, but that's a really interesting, I think area of research for C-band, radar, because I do believe that there are some, applications there that could be, incredibly useful. Career.
Because I'm actually doing the side data, I'm doing the forecast and things, so it's actually very helpful just to let you know so far. But I have a wonderful presentation. I have a quick question about, like, you talked a little bit about anomalies, like
Mhm.
basic basin. So just like for a second, focus on Western rules, right?
Mhm.
If you get a chance to look at like basin, like dive deeper on basin to basin accuracy, like for example, is it like you have a lower median compared to snowmelt in Sierra Nevada compared to the Southern Rockies? Did you like get a chance to look at how like your data accuracy
Mhm.
changes within like Western US, like the mountain range to begin with?
Yeah, totally. So Barreer's question, is kind of this idea for the validation. What was like the spatial, variability of like agreement and stuff that work better in particular areas? And something that we saw is, in the, maybe I can just click it through and find it really, really fast. For the very end of chapter 2, we have this plot. Yeah, it should be right about here. And you can see where our product, is usually earlier at the station or our product is later. Places like, the Sierras, you have, pretty low, bias relatively, within, 5 days or so. But the areas where this product seems to perform, the worst is where, there are 2 violations of this optimal performance. So if there's an area that, doesn't like agree with like the 50%, forest cover, like if there's a little bit too much forest cover, that's okay, so long as like temporal resolution is fine. But once you run into this problem where you have less than 20 meters of sweep, and you also have forest cover fractions above 50%, that's where those red circles, tend to pop up. So there's areas where there's low accumulation, where there's a lot of like canopies that are interacting, with the snow itself, but also the C-band radar. So a lot of complexities there. Yeah, thanks for your question. Oh, wow. Oh, Eli, nice to see you. Eli and Eli right next to each other. Eli, what's your question?
Yeah, so like stepping a little bit away from like the like methodological stuff and stuff, but like outside of the academic research,
Mm.
to be most excited to like hear about this research and
Yeah.
beyond that.
No, definitely. So Eli's question is, beyond the academic community and like just geeking out with people in the mountain hydro lab or whatever, who would I be excited about, talking, to with this research? I think, people, mostly like the USGS that are working more directly with these gauge basins that have, better ideas of like some of the more like fine scale complexity and site knowledge. I think would be nice for like the finer scale validation. I also think it'd be great to talk to people that do more of like the operational data assimilation, sides of things, and seeing how, this data can help, retroactively. One thing that might be interesting to look at, aside from this is just like the parameterization of like different snowmelt timing schemes, and does our runoff onset, provide any additional information beyond something like a snow disappearance state, in terms of what it could provide for these sorts of models. That's a good question, Ron. Dan.
Thanks for your great talk and all your contributions to the community. My question actually jumps off of what you were just kind of saying, but
Mhm.
Is there any perspective work that could go into using these essentially 10 years-ish of observations to sort of build more of like an extrapolative model that could look back further and try to make a product for a longer time series, or be used for operations with, let's say, a forecast of subseasonal estimates to try to, I don't know, use the information that you have to grow the data set itself.
Totally. So Danny's question is kind of focused on the idea of, we have like 10 years of data, like Sentinel-1 went up in 2014. Is there other like auxiliary information we can use to kind of, lengthen this data set in some way? Can we compare it to like other variables and such? And I think it's possible. Things that like this resolution, I think it would be like a little bit harder. Some of the longer collections of data that we have are things like, moderate resolution. So like more like MODIS, era, type work, Veer's, MODIS. You have, the Landsat record is probably kind of like the best you could, I think, do. Again, there are, it has its own issues with visual, or sorry, optical. Passive microwave data has been out for on the order since like 1979-ish. That's something that I think is exciting that I had on the future work slide is like, where can we fuse passive and synthetic aperture radar? Because while passive is extremely coarse, 25-kilometer spatial resolutions, they're more on the like 2 times a day in terms of like, resolution, where SAR very dependent on where you are on the globe, and how many satellites are up there, etc. So I think this would have maybe the most, for lack of a better word, like fusion capability with like passive microwave, and maybe using that as a means to like interpolate by using brightness temperatures at maybe like 37 gigahertz or something. So yeah, thanks for the question. Oh, Quinn, yeah. Oh, great. Oh, hey Ross.
Incorporate December, beginning of February, now into your algorithm and global data set. If so, do you expect the variables in chapter 3 to change?
I don't want to make you repeat that all again. I'm trying to pull up the so I can see. Sorry, can you repeat it one more time? Sorry, Ross. Okay. Yeah. Yes. Oh, I see. Yes.
So do you expect the results in chapter 3 to change?
Yeah, definitely. So not all, one of the complexities that we glossed over, right, was not all snow on Earth just follows these like very like ideas of like seasonal snow, right? If you go to places like the Tibetan Plateau, you might have like more like quarterly like snow. You might have it a couple times a year. You have places where summer is the season when there's the most amount of accumulation. High Mountain Asia in some areas, for example. So one of the complexities that this work kind of glosses over then is maybe it's not the best idea to just choose one singular date and time that you call the runoff onset, right? There's way more complexity there. And that's one of the reasons why, one of the earlier questions about like this wet snow, the near real-time applications, is another reason that stuff is really exciting, because you can kind of get at those sorts of cycles. Right, because you might have this time when like runoff onset really does happen earlier in the year, and then it accumulates again, and then it happens again. So I think this is a great like first pass at this sort of data set. But right, there's always more complexity that we can build in. So yes, I would imagine that including those instances of earlier melt. So having distinct time periods when this melt can occur, maybe one in spring and the other for these like early melt events is something that's, yeah, definitely doable. I think a little bit harder just because sometimes those snowpacks have been around for shorter amounts of time, and yeah, some problems with some masking there, but yeah, I think things could definitely change. Thanks Ross for your question.
Yeah, how many more?
Oh, one more.
Last
Is that good?
question, unless anyone has a burning one here in the eye. Okay, go ahead. You want to do one more?
Sure, yeah, I can do one more.
All right.
Unless it's hard, then no. Give me it easy, come on. I thought I planted these. Oh, pre-tone, hey, pre-tone. Okay, what thresholds do we use for the snow phrenology? So I think that might be getting at this idea that we talked about in the methods section, where we say, okay, seasonal snow means 56 days or more seasonal snow. what that's doing is that's approximating the Sturm and Liston idea of seasonal snow being snow that exists for at least 60 days. But the specific product that we were looking at, optical product, the Modus snow cover product, was something that existed on these 8-day scales because it was a product that kind of focused on getting a composite out of these 8 days of, at least maybe one acquisition with no clouds, right? So because of the way this data was structured, we use this 56 day threshold instead of like a 60-day threshold, because we wanted to be inclusive of maybe snow that was truly on the ground for 60 days, but because of how, the data set was set up, it wouldn't have gotten included if we just used the 60-day naturally. So that's where that 56 number comes from, which is odd. I understand. Yeah. I think when I was reading it too, I was like, man, I really should have just said seasonal snow. And then, if someone asked me, then I could be like, well, actually, like, it's whatever. But yeah, thanks, Preetam, for the question. That's also something that I think is exciting that we didn't get too much time to talk about. But snow chronology stuff is stuff that people are looking at even more recently.
All right, so let's thank Eric once again. If you have other questions, catch him when? Later today?
Sure. Yeah, I might take a nap after this, but yeah, honestly, whatever. But
In the future. Thank you.
Did you take a selfie? Thank you.